Okay, now we'll come to the key geometric argument, which lets you show that this space x tilde is contractible. Okay, it's contractible means that deformation retracts to a point. It will tell you that it's path connected and its fundamental group is trivial, what is called simply connected. Okay, sorry, there is a missing thing here. So this means, yeah. So let's look at the idea of this. So we want to show it deformation retracts to a point, and in this case the point is x0. So idea is we'll construct H, this deformation retract from x tilde cross 0 1 to x tilde. Okay, so inductively. So the crucial way of thinking, this is following Whitehead. So the first thing about this way of thinking is that you realize that homotopies are just maps, and you want to construct maps, you can construct them solving extension problems. Furthermore, the idea is that you can solve several extension problems inductively. We did this in another context where we divided into small squares or intervals. Here we go with the geometric structure that is inbuilt. Okay, so for example, in this particular case, we have our two spaces. We have our space x. Let's draw the space x here. So I'll draw it with a bunch of lines. So it looks like a tree. Yeah, so you have 4 guys branching out here, and so on. We'll not draw it for very long. Oh, this tree is wrong, of course. So let's draw it correct tree. So that was t-valent. But anyway, let me draw it this way for a certain reason. I'll draw a very flat kind of tree, and we won't go on for long. So here's the tree. And the reason I've drawn this is so this is x tilde. But x tilde across 0 1 can be drawn in a very similar way, which is I'll just take a tree, again a purple one, which sits kind of above this. Okay, goes here, goes here. So this is the copy of x tilde across 0 1, and it is deliberately supposed to be sitting above this. Yeah, and let's look in this light cyan like color, the edges sitting above this. So now this begins to look a little bit like what I wanted it to look like. Here it goes, here it goes. So the idea here, which could have been better executed, is that you x tilde across 0 1 looks like a graph sitting this way. Okay, so this is x tilde. This whole thing is maybe I'll call this is x tilde cross 0 1, and the purple colored one is x tilde cross 1, and this is x tilde, which is also x tilde cross 0. And I want to define a map, and I already have the map defined. Okay, so we are given H on x cross 0, okay, x cross 1. So here it has to be identity, here it has to be the constant map E, and also on E cross 0 1. And here also it has to be the constant map E. Okay, so let's write that out here. H of x comma 0 is going to be x, h of x comma 1 is going to be E. Both of these are for all x in x tilde, and for all x in x tilde, and h of E comma s is going to be equal to E. So maybe this should really be T for all t in 0 1. And I want to define it on the rest of the space. Okay, so what we'll do is we'll first define H on vertices V cross 0 1, and I should say v tilde, the vertex set cross 0, 1. So we'll define it in all these vertical guys. And there'll be some fairly clear way on how to define it. Okay, so there are vertical guys because of my, there's a missing vertical line here. So for example, there was a vertical line here. We'll define it on all these vertical lines. Okay, so there are vertical lines here. This one I think got erased here. So we have all these vertical lines. We'll define it on the vertical lines based on what it is at the vertex. On top it has to be E, and on this vertical lines it's kind of forced by these things. We'll just take a path, a natural path on this, and then after that we'll extend to all the squares, and this we have to show is possible. Okay, the first one is possible simply because it's path connected. So we want to define it on the vertical lines, and we want to define it on the path verticals. Okay, so let's just recall for this setup. Recall what vertex set is. Vertex set is just the set of all words L1 Ln, and L1 Ln is a reduced word. Okay, this is a reduced word in alpha, beta, so and so. Okay, now so this is given by, there is a path to L1 Ln, namely we look at E L1 L1 L2. So path here is just sequence of edges. L2, L3, etc. Okay. And what we'll do here is, so we are going to define our map in a moment, but just as a general principle is we'll identify edges with their paths. Okay. So edges correspond to paths. I already mentioned this previously. Okay, so this will let us define things precisely, and for that we'll look at a fresh picture. So let's look at it. The previous picture is also nice. We'll go back and forth between the two, but let's look at a simpler picture here, just in terms of lines. So we have a path. So let's take now the genuine Cayley graph. It goes this way, this way, this way, this way, and let's look at, for example, the point there. Okay, so I have continued this, not at all balanced in any way, just to give a rough idea. And let's take a purple point. Okay, this one. So I don't want it a line, just a point. So I have my vertices here. They correspond to reduced words. Okay, and according to my previous picture, this word here is going to be equal as usual using these conventions. This is going to be alpha. So this was alpha, 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 beta, for example. And I have a path that goes to that. Namely, I look at alpha, I look at this edge, and then this edge. Okay, so let's give that some kind of name. So for W in whatever I call it, V tilde, you let's call that lambda W. Lambda I've been using for single letters, so it's called it eta W, or so this be the path E L1. So if this is L1 Ln, so E L1 star L1 L2 star Ln minus 1 Ln. Okay, so it's just the path which goes up to these things. Okay, so now I want to so this is a path. I am going to be casual about associativity here. I'm not going to be so strictly speaking, we have to decide that this might be if this was left associative, which is normal, this takes half the time, and then this whole thing takes only half the time, etc. This will take 1/2 to the n time, but I'm not going to bother because we can always reparameterize, and we are going to consider things up to homotopy only. Okay, nice. So how do I define the thing on what was previously purple line, which goes from up from here to here? Remember, on top, so at the bottom you map to yourself, which is alpha, alpha bar, beta, and on top you have to map to E. So we'll just use this path eta bar. Okay, so you define H on the vertex W at the height S to be, well, we'll take the we have to start here and go back to the origin. So I'll take eta W bar of S. Okay, so again, now it's worth just sort of scrolling up and seeing. Remember, in our picture, so this is going to be one of these vertical lines. So on top you have E, and at the bottom you have W. So I just take the path to the origin. So when I go up here, I just use the path from W to the origin. Okay, this makes things nice and canonical. And this is well defined. These are anyway disconnected. So I mean, the various edges of this form are disconnected. Okay, and hence we have H. So this will give me H on. So now we have H on everything except the squares of these forms. Okay, so finally we extend H to squares. And now if what are these squares? They are of the following form. Okay, so now I call this path W, but I have to go to the next step also. Okay, so let's take a square, and that square is going to have this edge, the two maroon lines over it, and the edge on top. Okay, my color changed unfortunately, so there may be this. Let's go back to the previous color. Let's erase all this. Let me go back to my previous color conventions, if not quite straight enough. Here's a black line. So what I had was that on top, the guy above was maroon. So these were not maroon, but I'm not going to change that. So what I had is on top, I had this, etc. And I had these cyan colors going from here to here. So I've already defined things on these cyan lines. Okay, the black lines is defined earlier, it's the identity. So here these are defined. These are in fact your eta of W bar, and here the things are defined, they're E. Here they are X itself, the identity map. And so what we have to do is define it on the square. Okay, so extend to squares. What are the squares? Hence we look at W and W lambda. So these are both reduced. So I think of this as an edge cross. Okay, so this is the edge W lambda. So I'll put a square bracket on this. So let me then be a little more explicit. So given W lambda, W and W lambda reduced, that's what the edge is. We might as well consider the outward edge. I'm looking at the interval W lambda cross 0, 1. Okay, and H is defined on its boundary. And let's see how it is defined on its boundary. So here let's just look at this square. Okay, so here it is simply E on top. On the bottom it's going to be equal to this guy goes to W, this guy goes to W lambda. It's going to be W lambda. It's going to be this edge W lambda. Here it's going to be eta W bar, and here it's going to be eta W, that is in the upward direction, it's going to be eta W bar. In the upward direction here it's going to be eta W lambda bar. Okay, so now let's go counterclockwise around this circle. So suppose we go this way. Okay, so on we'll give this square a name. We'll call it D2. It's a disk. On boundary D2, we get the loop. Okay, so let's call this point here maybe S1, 1, and we identify the boundary of D2 with so this is 1 in S1, which is boundary D2. So what is the loop we get? We get first of all E, and now we get eta W bar but in the upward direction, but in the downward direction we get eta of W. So I'll expand out eta of W here. It's going to be EL1 star L1 L2 star all the way to ln minus 1 ln. And then what happens after that? We have W going to W lambda. So this W is L1 to ln, and this is ln plus 1, let's say. Okay, star ln plus 1 star, and I have to continue on the next line, eta W lambda bar. But what is that? That is going to be ln plus 1 bar. Remember, when I invert, I take each edge and reverse it. And I reverse the order also. So I'm looking at a path going backwards from this guy. So it's going to be this edge reversed. So that's ln plus 1 bar. Okay. Star ln minus 1 ln bar, etc. all the way down to, we come back by the same path as we came, because it's we have chosen the reduced word. We don't have to prove uniqueness of path or anything. We have by convention chosen the word, and the last of them is going to be the first letter reversed. Okay, let's call this theta. Okay, so what do we see here? Well, we see something nice. Namely, we see, it's quite obvious. So theta, which is, let me write it out again in full, E star EL1 star etc. star ELN. That's because I went from E to the vertex ln. Okay, star. Now I go on to the next guy, which is ln plus 1 star. Now the things have to be in reverse order, because I'm going back to the origin, and so this is eta W lambda. W lambda is L1 ln plus 1. So when I take the bar of this guy, I have to take the last edge of this and reverse it, which is going to be ln plus 1 ln bar star etc. and all the way down to the first edge of this, which was E L1 bar. And of course this is visibly identity. Okay, E alone was okay. This is homotopic to the identity. So what we see is on each square where H is defined, this is homotopic to the identity. So we have a little exercise here. So I'm not going to break momentum by proving this. You can read it up. So this the following proposition. Namely, if I look at any function f from S1 to x extends to capital F from D2 to x, if and only if I look at f star of the boundary S1. Okay, so the boundary S1, you have to think of it appropriately. That is actually the generator. Might as well be formal. This is 1 in pi 1 of S11. So f star of 1, this belongs to pi 1 of the image, and the image here is going to be x, but with base point f of 1. So the base point doesn't matter, is trivial. Okay. So if and only if the boundary is homotopic, you can think of it fixing endpoints or even freely homotopic, that is not fixing endpoints. There are various characterizations of it. Okay, they are quite easy to prove. So we have this proposition if and only if this happens. So thus H extends on all squares. And we are finally done. Okay, so by gluing lemma, because we have defined it on all squares and it coincides with previously defined continuous function. So by gluing lemma in from set topology, H is continuous. Okay, so and as required. Okay, so what we have managed to prove is that your identity map is homotopy equivalent to the constant map. Okay, that is, we deformation retract, fixing the constant. So that is to say the space itself deformation retracts to a single point. Okay, so immediate corollary of this is pi 1 of x tilde E is going to be equal to the identity, is going to be the trivial group, because it deformation retracts to a point and a point has trivial fundamental group. Okay, so now this is really the main work to be done. After that we can quite easily calculate the fundamental group of x tilde.